Now let's move on to the neural network models. Neural network models are the most widely used deep learning models. Oftentimes, they are just called deep learning models. Many times when people talk about deep learning models, they actually refers the neural network models. This diagram here represents a typical one-layer neural network model. In this neural network model, we have several different layers. First, we have an input layer. The input layer basically provides the information about the input of the predictors. As we know in the active data set, we have 4 predictors: grouping, variable, age, gender, verbal test score before training. And then in this model, we have one hidden layer here. They are represented by H1, H2 to H32. Each H here is called a latent node, or is called a hidden node. Each node represents one variable in the neural network model. I remember in latent variable models, if you are familiar with that, we have latent factors. So each of these latent node or hidden node can be viewed as a latent variable. And also there's a connection between each input and each latent or hidden node here. So therefore the input and the nodes are fully connected. For example, we have arrow from X1 to H1, H2 to H32. Similarly, we have an arrow from X4 to H1, from X4 to H2, and then from X4 to H32. And then we have an output layer. So here I call it O. In the output layer, I only have one node, but for other models, you may have more than one node, just like in the hidden layer here. So where do we include our output data in this model? As we know, like in our active data, we have an outcome variable that is verbal test score after training. So we can also plot the outcome here. And typically, you may not see this in a neural network model diagram, but I included this here for illustration. In some models, you may not have an outcome variable at all. In that case, we call it unsupervised learning. In our case, we do have an outcome. So this model actually represents a supervised learning model. Again, like in these models, we have 4 predictors. We can represent the predictors as S1, Xj, j equal to 1, 2, 3, 4. And again, like I only plot one X1 here, but since we already recoded the X1 to 3 dummy-coded variables, and for fully representing the model, we can change this to be X11, X12, and X13. And each of these X1s are fully connected to the hidden nodes here too. And we can use HK to represent the nodes in the hidden layer. So HK equal to for the HK, k equal to 1 to 32. Each hidden node can take a value. The value of the hidden node is calculated based on the input, actually. So for example, H1, those are associated with the 4 input X1, X2, X3. To calculate H1, we need to know the association between X1 and H1. Just in the regression analysis, we need to know the regression coefficients so we can look at the outcome variable, the association between the outcome variable and the predictors. And X1, X4 can be used as predictors of H1. And the coefficients here usually are called weights. So we may have many different weights. So this is the first layer. I use 1 to represent the first layer. From X1 to H1, so I use another 1, 1. So this means the weight from H1 to X1 to H1. And similarly, we may have W as the first layer from the second predictor or the second input to this first node. I use W 1 to 1. You can use different other notations, but this is one way to do that. Similarly, I have in this particular example, H1 is a linear combination of X1, X2, X3, and X4. So if we know the weights here, we can directly calculate the value of each one. Similarly, we can do this for the other hidden nodes. For 32, we only need to change this to be X1 to (34) node. Similarly, I add them together. Okay. More compactly, we can use this. In addition to the input and the weights, we can also have an intercept, BK here. So the intercept is more like the intercept in the regression analysis. In neural network analysis, it is also called bias or offset. In this workshop, most of the time I may call it intercept here. So here we use a linear combination of the input, but there might be a nonlinear relationship between the hidden node and the input. We can use any function to transform this input to the output. Here is the hidden node. For example, we can use a function g to do a transformation. This g can take many different forms. This function is also called activation function. Linear function itself is an activation function. For the linear activation function, basically we have this association. So this gt basically is equal to t. There are several widely used nonlinear functions or the nonlinear activation functions. For example, sigmoid is one of the most widely used activation functions in the initial development of deep learning methods. The single mode sigmoid activity function is also called logistic activity function, takes format of this, because GT equal to 1 over 1 plus E with power negative T. And clearly from this function, it can change any value into the interval 0 and 1. So T could take a value from, for example, negative infinity to positive infinity. When it's equal to negative infinity, so that's basically 0. When it's equal to positive infinity, we have 1. So if an outcome, or if you want to transform this value to be transform this to get a value for the hidden node in the interval 0 and 1, and then we can use this activation function. Another widely used activity function called the hyperbolic tangent activation function, similar to the sigmoid function, but it now transforms your data to be the interval of -1 and +1. Currently, one of the most widely used activity function called the ReLU, rectified linear unit activation function. What this function does, it takes this format. So if your t value is smaller than 0, then this gt will be equal to 0. Okay. Otherwise, if t is larger than 0, and gt becomes a linear function. Just like in the linear activation function. And this activation function is proved to be very useful in many deep learning models. So that's the association between the input and the first hidden layer. Okay. From the hidden layer to the output layer, we can also have similar associations. For example, this output O could be a linear combination of all those 32 hidden nodes. Okay, so we certainly also need to add the width here. We can call the W21, W22, and so on. So this will be W21 times H1. This could be W2 32 times H33. Okay, so the value of the outcome can be calculated from the hidden nodes. As in the association between the input and the first layer of hidden nodes, we could also add the activation function here. Like if the activation function is linear, so basically equal to this. Otherwise, we could do a linear transformation. We can also have a bias or intercept here when we look at the association between O and the hidden nodes. Certainly, in this very simple model, we only have one hidden layer. We can have more complex models with 2 hidden layers, 3 hidden layers, or even 20 hidden layers. So this is also the reason why the neural network model is called a deep learning model, because the layers can go very deeply in the model. If the weights are known, so we can calculate all the value directly. For example, given a set of input, given the weights, we can calculate the values for all the nodes, whether it's in the hidden layer or it's in the output layer. Right? But as in regression analysis, most of the times we don't know the width here. So therefore, we need to find a width to estimate those widths. Now let's talk about how to estimate those widths. Certainly, the biases or the intercepts are also not known. We also need to estimate that. We can give any value to the width as in regression analysis. However, we may want to get a better set of widths. In regression analysis, oftentimes we want to minimize the difference between the predicted value and the observed value so that we get the least square estimates for the regression coefficients. Similarly, we want to do the same thing for the neural network analysis. For example, we may consider a set of weights that minimize the difference between the output from the neural network model and the observed outcome values from the data set. So that's basically, if you look at the association here in the model, so we have y, I, so y is observed, right? So this is our data set. We may have a OI is calculated from this input, assuming the weights are known. Okay? So in this situation, we have a difference between the predicted value, we may call it, from the neural network model. And then we have observed value from our data. So naturally, we would expect a good set of weights would minimize the differences here. So that's the whole idea of estimating the width for the neural network model. That's also the idea used in the regression analysis. For very simple problems, we can minimize the difference here analytically. For example, suppose we only consider one predicted age, and then we use a simple regression with slope only. So our regression model will become y equal to beta times xi. So this is the population model. So this xi is age, and this y is the verbal test score after training. I didn't include the intercept here because assume we already standardize our data, both age and outcome. So in this situation, the intercept would be 0. There's no need to estimate that. I just want to use this very simple example to illustrate how we can estimate the width of the parameters in a model. Okay. In this situation, the predicted value would be b times xi. So b is an estimate of beta. Okay. And if I expand on this equation here, I have this. As we know, both xi and y are observed. So which means this sum of y squared is a number. The sum of y times xi is also a number. Sum of x squared is another number. And if I plug in the values into this function, I have an equation with b. B is the regression coefficient I want to estimate. So this function fb equal to constant times b plus this number times b squared. So this is the quadratic function. Those values can actually be calculated using the R code here. Now I have a function. I want to plot it to see what it looks like. So this is a plot of the quadratic function fb. And remember earlier, we hope we get the best b that can minimize the difference here. The minimize would be the minimum value of this function would be here. Right? So if we want to get the best estimate for b, we want to find this b value, because this will give us the minimum value for the difference between the predicted value and the outcome value. Certainly, if we can generally plot look like this, we can easily find this value. There are many different ways to find this value. This plot method is actually called profile analysis. So we can plot the FB value for each B, and then we find the minimum value for FB, and then the associated B value. So that will give us the estimate. But oftentimes, it may not be that simple. So if we cannot directly plot this, how we can do this? And another way to get the estimate of B is if we take a look at the figure again, notice that this is the bottom of the figure. The bottom of the figure means if we put something on this curve, like we put a small ball here, and it will roll down to the bottom of the curve. At the bottom of the curve, the ball doesn't move anymore, which means it has a speed equal to 0. Okay, so therefore the minimum value for this curve happens when the tangent line of this curve is equal to 0. The tangent line is also the rate of change or rate of growth. We typically use the first derivative to represent that. So therefore, the value that minimize the function is actually happens at the first derivative of this fb function equal to 0. And the first derivative of this function is given here. So this is from our calculus class. And we can solve this function, and then we found our b will be equal to the sum of product of x and y divided by we should have a sum here, sum of xi squared. So this gives us the value negative 0.34. This means when b is equal to negative 0.34, the function fb has the minimum value. And actually the minimum value is 2024.47. For this simple problem, we actually get the analytical solution. So that's the exact solution we can get for B. However, in many situations, the problem is much more complex than this simple example. In that situation, we cannot get the solution numerically, analytically. Oftentimes, we have to use certain kind of numerical optimization algorithm to find an estimate for B. So one of the algorithms is called gradient descent algorithm. It is very widely used in deep learning. So let's see how we can use this algorithm to find the value for B. Okay. Now, suppose we cannot get the analytical value for B equal to negative 0.34 anymore. But let's take a look at the curve again. Okay. Although we cannot directly say, okay, the B value equal to negative 0.34, we may think about, okay, we may start from certain points For example, I start from here. 0.4 could be some kind of value. I can try initially. I may say, okay, my B value should be 0.4. Given 0.4, I can calculate FB, right? And FB here. Clear FB is far away from here is not the best possible value. But I want to see if there's any algorithm. Following this algorithm, I can move the value from 0.4 to here, right? Maybe like I can move here from here, I get another value, and then move to here, get another value. And then after a few steps, I actually move to the value around negative 0.34. So that's the idea, actually the idea of the gradient descent algorithm. Right? Certainly, we want to find like a systematic way to move from a initial value to the best possible value. One way to do that, or one intuitive way to do that is, I just move this like in a small step each time. For example, I can decrease the value of B by 0.1 if I start from 0.4. But in my example here, I actually start from a value B equal to negative 0.4. So which means I actually start from here. So if I start from here, I want to move to here. Right? So in this case, I can increase the value of B each time by 0.01. So which means each step, I increase the value by 0.01. So therefore, if I start from negative 0.4, then next value, I will have negative 0.39. And then next value will be negative 0.38. So I can keep doing this. We would expect if another value is better than this current value B, the function of FB should decrease, right? So for example, if I move here from one value here, I would expect this FB will decrease. And if FB increase, then it's not good, right? And we can also see that eventually we remove the best value here. This will give us a minimum value for FB. And if we increase the step again, so we move away from the best value. In that situation, we will see the increase of FB, which means the FB should typically first decrease and then increase, and with the increase of B, right? Then we need to decide when should we stop moving along this FB. We can stop when FB start to increase. So that would give us maybe the best estimate for the value. So the criterion to stop the algorithm, basically, we check whether FB is increasing or FB stopped decreasing. We can actually use the code below to find the value for B using the method I just described. So we start from this function, and then we start with B equal to negative 0.4, and then actually try to step function 0.01, which means the first value 0.4, and then I have negative 0.399, and then 398. Okay. And I calculate the function of FB when B is equal to negative 4. So that's giving me the value here. Then I use a loop, while loop. In this while loop, each time I add a small step to my value B. Okay. And remember, if b start from the other side of the curve, we can use minus step function, but minus the step value. Then I calculate my new FB function value. Then I will check whether my new FB function value is larger than the previous value. If it's larger than the previous value. If it's larger than the previous value, which means my FB is increasing, then I should stop. Right? I should stop my algorithm because I probably found the best value for B. And otherwise, I set my current FB value as the new FB value. So, for example, if I start from negative 0.4, then I try the value negative 0.399, and then I found the FB value associated with negative 0.399 is smaller. Then I set my new FB value to be this value, and then I try this algorithm again. Okay. If I keep trying this until I stop doing it, so which means my new FB is larger than the previous FB, I will stop that. This will give me the where I stop the algorithm will give me the best possible value for FB for the B parameter. Here my B is equal to negative 0.339, which means at here I probably get the minimum value for FB. So that's 2024. Compare that to this one, is smaller than this one, right? So which means this B value is certainly better than negative 0.4. And from the algorithm, we can see if we can improve the step value, so which means if we can choose a good step value, we can improve the efficiency of the algorithm. Because for some step, we need to do the calculation many times. For some steps, we may only need to calculate the value for FB a few times. How to choose the step is critical. In this example, we fix the step as a certain value. Another way to do that, maybe we want to do is at the different steps, we want to add a different value. For example, at here, maybe we can move to this faster, so we can choose a step like this size. But when we move to here, we may choose a step smaller size because we don't want to skip this value. We move to here, right? So therefore, we can, if we can do this, we may be able to improve our algorithm. Okay. So one algorithm actually focus on how to decide the step here. From the curve, we also see if we want to move to this bottom as fast as possible, we should move along this tangent line here. So which means we should move around the first derivative here. The first derivative is calculated by this. In this situation, if we have a value B at the current step, for the next value of B, we can use B minus the first derivative of this function. This typically gives us the faster speed to get to the bottom of the curve. Many times we don't want to directly use this step here. Instead, we add something called learning rate to it. So basically, we multiply the first derivative by a learning rate R here. By choosing this R, we can control the performance of the algorithm. For example, if we use B equal to first derivative times R. Intuitively, if this R is large, so which means we have a large step here. For a large step, we may move faster to the bottom of this curve. But at the same time, if you have a large learning rate, maybe like we actually can jump beyond this best value to here and then here, right? So in this case, it actually won't help the algorithm. For smaller learning rate, so we move slowly, maybe like on this curve. But in this situation, it will be more difficult to skip this best value here. So typically, in this kind of algorithm, we may choose, we may try different R's to see which one works the best. Let's see how we can do this in R. So here I use the code here. This gives you the first derivative because we know we need to calculate the first derivative. Then when I update my B here, I use B equal to B minus the first derivative at B multiplied by learning rate. Here I specified my learning rate as 0.0001. You can choose a different learning rate after the workshop to see how this algorithm works. Here I also use the slightly different stopping criteria. Earlier, I choose like look at FB, and if FB increase, then I stop my algorithm. Here I actually look at the difference between B's in two steps. So this is previous B and this is current B. I would expect like in my algorithm, my B won't change much as the best value. For example, if exactly as the bottom, my current B and my next B would be the same. So the difference will be 0. But then when we use an algorithm, many times we cannot get the exact estimate, but we can get a good enough estimate, which means my B will be infinitely close to the best value, but although it will never reach that. However, in practice, the difference maybe is not that important. For example, suppose my best value would be negative 0.34, then my estimated value could be this. And although it is not negative 0.34, but the difference can be ignored. Okay. I'm not going to explain the code here line by line, but you can try this out after the workshop. And if you have any question, feel free to email me to ask. So basically, for this algorithm, I moved my values 8 times. Then I found my best B value here based on the algorithm is negative 0.340. The minimum value for this function is this one. This about the same as the value we got earlier. And it is also very close to the value from the analytical solution. In neural network analysis, we need to estimate the width and base. Although the neural network models would include more parameters, but the similar algorithm can be applied. Of course, it can be much more difficult to get the parameter estimates. To summarize, to estimate the unknown parameters in neural network analysis, that would be width and base. We usually start with a guess of those values. For example, we may use our best guess as negative 0.4 for our regression coefficient there. And once we know the width and the base, we can calculate the output based on the neural network model and the input data. Remember, once we know the width, the hidden layer can be calculated as a linear combination of the intercept base plus width of the input of x. Right? So we add this them together. So doing this calculation is straightforward. And then we have O as a function of this h. So therefore, we have the predicted value based on the input and the width and the base of the model. Then we can calculate the difference between the output here and the observed data, and then we square that by minimizing the squared difference. Then we can get the best estimates for the width and the bases. Of course, this is the iterative process, as in the very simple model I showed earlier.